All right, guys, so sorry I was interrupted by that phone call. Okay, so we had just gotten done talking about calcium with its 2 valence electrons. Let's move on. So beyond calcium, we're going to skip the transition metals. So once we get to the transition metals, we will have gallium, which will have 3. Then we have germanium, which has 4 valence electrons. And then we have arsenic, which has 5. And then we have selenium, which has 6 valence electrons. And then we have bromine, that has 7. Hopefully you're seeing a pattern here. And then we have xenon, that has 8. Okay. And then last but not least, we're going to go one under potassium. We've got rubidium. We have 1 valence electron. Strontium with 2. And we're going to skip over the transition metals. Underneath gallium, we have indium, which has 3. And then we have tin, that has 4. We have antimony, which has 5 valence electrons. Then we have tellurium, that has 6. And then we have iodine, which has 7. Gosh, if my pen will work. And then last but not least, did I skip? Yes, I did. This is xenon, that has 8. Ooh, did you guys see my mistake there? I skipped. So let's make this right. This is not xenon in here. In here, it is krypton. And we will have 8 valence electrons with krypton. Okay? So hopefully by now you realize that for the main group elements, notice in the main group, we do not use the transition metals. It's just groups 1, 2, 13 through 18. So in group 1, all of these elements will have 1 valence electron. Group 2, we have 2 valence electrons. Group 13, we have 3 valence electrons. 14, 4. 15, 5 valence electrons. 16, 6 valence electrons. 17, 7 valence electrons. And 18, 8 valence electrons, with the exception of helium, that has 2. Okay? All right. Let's look at our next periodic trend that we are going to look at. We are going to look at atomic radius. Now, when we measure an atom for atomic radius, remember we have kind of the electron cloud model. We really don't know where the edge of that atom is because those electrons are kind of cloud-like. So how do we actually measure the edge of an atom? So what we do is we take 2 atoms that are bound together, and we measure the distance between the 2 nuclei. So we get the distance between the nuclei. And if I do the distance between the nuclei like this, and I divide it in half of that distance gives me the radius of an atom. That is the only way we can really get a radius of an atom. Because of the electron cloud model, we really can't define an edge of an atom unless it's bonded to another atom. Okay? So we take half the distance between 2 nuclei that are bound together, and that creates our radius measurement. Okay? So let's look at the size as we go from left to right across a period in the periodic table. Now, if you remember, the periods on the periodic table were the rows right to left. So let's look at our first period. Our first period is really just helium and hydrogen. So we're going to look at our second period here. Lithium is where we start on the left, and fluorine is where we end up on the far right. And as we go from left to right, you'll notice that the size of the atom goes down. Same thing for our third period. Sodium is where we start with at our left. Let's look at our periodic table. Did I not put my periodic table up? And chlorine is where we look for it on the far right. Notice that third period, we still have the general trend of the atoms getting smaller. Now, think about it this way. The atoms are indeed getting smaller. Okay, or they decrease in size. Okay, so why is this so? Usually when you put more stuff, think about it. Every time I put a new element on these, I'm putting in an extra proton and I'm putting in an extra electron, and sometimes I'm even putting in neutrons. So wouldn't you think with more stuff that it would become bigger? But it actually becomes smaller. I want you to think about it this way. Remember, the nuclei of an atom is so small. All those protons in the nuclei, every time we add another proton to that nuclei, we are adding the positive charge to that nuclei. The electrons out here are so spread out, so spread out, that the effective charge in this nucleus becomes greater than the effective charge of the electrons. So because the charge per volume ratio is so great with the protons in the nucleus, the protons are able to suck those electrons in the more protons that we have. So the protons in the nucleus have a greater effective charge. And pull the electrons in. As one goes from left to right through a period. Okay, so the protons are able to pull those electrons in because all those electrons are going in on the same energy level. And the protons are much closer packed than the electrons are. So the protons have a better effective charge to pull those electrons in. Okay, let's look about the trend as we go from top to bottom on a periodic table. Okay, so we're going to look once again on the alkali metals group. We're going to start with lithium and go through cesium. Notice as we go from lithium, this is the top of the periodic table. This is the bottom of the periodic table. What happens to our size as we go from the top to the bottom? It gets larger, right? Let's see. Gets larger or increases. Why do you think it gets larger? Why does it increase as we go from the top to the bottom of the periodic table? Okay, I want to draw something for you. Remember when we did the Bohr models? Lithium had, well, hydrogen. This would be hydrogen. Lithium. Let's draw sodium. What do you notice as, and let's draw one more, potassium. What do you notice about each time I go down the periodic table? What happens each time? I add another layer. So each period of the periodic table adds another layer of electrons. And eventually, once we get several layers of electrons between the nucleus, this little thing in here is going to be the nucleus. Don't you think electrons next to electrons, what happens when I have negative charges next to negative charges? They repel. Eventually, we get so many layers of electrons through here, we get electron repulsion. So the more layers we have, these outermost layers of electrons actually get kind of pushed out from the nucleus because the other layers of electrons repel them. Okay, so the more layers of electrons, the more, oh wow, the more electron to electron repulsion we have. That's called electron shielding. So these inner electrons shield the outer electrons from the pull of the positive nucleus because electrons next to electrons repel each other. Okay, next thing we're going to talk about. Okay, so this is just another periodic table of elements that we can mark up. These are some puns for you. Let's talk about ionization energy. Ionization energy is the energy it takes to form an ion by taking one electron off of an atom. So to form a positive ion, an electron must be removed from a neutral atom. This requires energy. The energy is needed to overcome the attraction between the positive charge of the nucleus and the negative charge of the electron. Ionization energy is defined as the energy to remove an electron from a gaseous atom. Think of ionization energy as an indication of how strongly an atom's nucleus holds on to its valence electrons. High ionization energy value indicates that the atom has a really strong hold on its valence electrons. Atoms with a large ionization energy or ionization value are less likely to form positive ions. Why isn't this letting me write? Okay, because remember, if I take an electron away, I will have more protons. Likewise, a low ionization energy value indicates that an atom will lose an outer electron really easily. Such atoms are likely to form positive ions. Okay, so let's look at this trend. So hydrogen, it's pretty easy to pull that electron off. Helium is a lot harder. Then if I look at the next period, lithium, it's even easier to pull it off than hydrogen. And then neon, as I go up, it gets harder. Sodium, it's about the same as lithium, a little bit easier. And then argon, through that period, it gets harder. Potassium through krypton. Notice as I go through each period, it gets harder to pull those electrons off. The elements that are the hardest to pull off, notice the ones that are the hardest to pull off, those are the noble gases. We have helium, neon, argon, krypton, and xenon. Those are the hardest ones in each period to pull the electron away from. So why do you think the noble gases have such a high ionization energy? Think about size. Don't the noble gases have the smallest radius of their period? They have the smallest radius of their period, which means that the electrons are closest to the nucleus and able to be felt and pulled in by the protons in the nucleus the best. So why do you think the alkali metals have such low ionization energy? They have the largest radius. The electrons are far away. Those valence electrons are really far away. Okay, so let's do a few things here. So let's practice. Actually, we'll have to finish this video later.